Good morning, everyone. My name is Young Ri. I'm chair of this session. Today, our session title is Humans and Collaboration. And today we have four, four papers. Mm, and so each paper has 15 minutes, totally 15 minutes presentation, uh, 12 minutes presentation, and 3 minutes for question and answer.
Okay.
So I will ring this bell at 12 minutes.
Okay.
So, so let's begin our session.
Begin.
The first presenter is Hao Jong Yang.
Yeah.
His title is Exploring the Influence of Crowd Size Across Different Tasks on the User Performance, Experience, and Social Pressures in Shared Virtual Environments. Let's welcome.
Well, hello everyone. My name is Hao Zhongyang, and I'm from the State K Laboratory of Virtual Reality Technology and Systems at Beihang University, China. As virtual reality technology evolves, we are seeing a rapid expansion of shared virtual environments, or SVEs. Unlike early VR experiences that focused on individual immersion, the platforms such as VR Chat or Horizon Worlds increasingly support multi-users, collected experiences where people interact, communicate, and even perform tasks together in the same virtual space. The video here shows one such example, users gathering, exploring, and engaging in shared spaces, which illustrates how social presence has become a defining feature of modern VR. In SVs, human perception is not static. It constantly adapts to both the social and task context. Virtual environments don't just display information, they actually modulate our attention, our behavior, and our sense of presence. The social facilitation model suggests that a person's task and the presence or characteristics of an audience or crowd together influence perception and behavioral responses. Previous studies have explored these mechanisms mainly in traditional video games. However, in immersive VR, where the sense of co-presence is much stronger, the dynamics could be even more complex and pronounced, which motivates the research I will present next. Some related work have investigated avatar appearance, behavior, and other influencing factors in virtual environments. For example, they investigate the appearance of avatars can affect users' avoidance behavior and the avatar transparency and gather behaviors and crowd organization and behavior and reactions and so on. Beyond individual avatars, prior work has examined crowd effects in VR. For example, studies look at audience behavior in lectures, social anxiety in public speaking, avoidance distances when walking, and navigation through dense crowds. These findings show that crowd presence and behavior shape user perception and performance. Yet, the ambient social context, the visual presence of avatars without interaction, is still largely underexplored. And some studies mostly examine the crowd effects in specific contexts, like public speaking or navigation. However, in VR, users perform a variety of tasks, each with unique behavioral and perceptual patterns. So the task difficulty can modulate perception, and the task characteristics can shape experience, so the effect of surrounding crowds is not universal. According to the social facilitation model, both task and audience factors influence user perception and reaction. And building on this, our study asked two research questions. How does crowd size affect performance, experience, and social presence within each task? And how do different VR tasks influence perception of virtual crowds, and does this vary with task demands? Mm. We designed a controlled VR experiment with a 3x3 within subject design. And the setup includes three representative VR tasks, each differing in cognitive and motor demands. And three levels of crowd size to represent different levels of virtual social presence. The participant will navigate in this island and each trio happens within a defined activity area. It can be divided into two parts. The crowd area, as shown in yellow, where avatars are placed as a social context, and the task area, shown in pink, where the participants perform the task. Our first task is spatial locomotion, which evaluates how efficiently participants can navigate in SVAs. As you can see in the video, the participants start at the edge of the activity area and goes to a blue tagged circle, and a new one appears at a random location. The second task is memory sort, designed to test the user's cognitive processing and memory performance in a complex visual environment. The participants first walk to a small box and press a button to start the trio. 5 objects are then displayed for 10 seconds. The participants need to memorize them carefully. After that, they move to another area filled with 80 mixed items, and their goal is to find and select the 5 tagged items. The third task is motor coordination, adapted from the VR game Saber. The participants will receive 2 virtual lightsabers, 1 blue, 1 red, and select incoming blocks of corresponding colors as they appear. And our card design, first to ensure realistic layout, we maintained a meaningful interperson distance of 1.2 meters between avatars. We manipulated the crowd size across 3 levels to represent different degrees of virtual presence: small, medium, and large. There's first person and the third person view. And we collected both objective and subjective measures to evaluate participants' performance, experience, and social presence. The objective measures include navigation time, accuracy, or percentage of blocks intercepted, and average heart rate. The subjective measures include the perceived crowd counts, the workload, task experience, social presence, and interview responses. We recruited 24 participants balanced by gender. Each participant completed 3 tasks under 3 crowd set conditions, resulting in 260 valid trios in total. For data analysis, we performed both 2-way analysis to examine the effects of task by crowd size and 1-way analysis for task-specific variables or further explorations within each task. About task performance, our memory sort showed a significant effect of crowd size. The medium size and the motor coordination both had a significant difference. And the participants were asked to estimate crowd size based on their subjective impression, and the large size showed significant differences. In memory search, the participants perceived fewer avatars than in spatial locomotion. About workload, the 2-way analysis of task by crowd size, we found that task type affected all workload indicators. And the 1-way analysis to see how workload change within each task. For spatial locomotion, large crowds increase the temporal demand and effort. For memory search, mental demand increased as crowd size grew. And interestingly, for motor coordination, participants had the worst performance under medium size. About task experience, the 2-way analysis of task by crowd size, we found that task type had a main effect on all task experience indicators except presence. And for motor coordination, there was a significant interaction effect between the task and the crowd size. About social presence, in the 2-way analysis of task by crowd size, we observed that crowd size had main effects on many indicators. And when examining each task individually through 1-way analysis for motor coordination, 4 indicators showed significant differences. And the participants' preference and interview feedback. On the left, we have the voting results for preferred crowd size. We can see the motor coordination, the panel thing. 12 prefer the small size, but interestingly, 7 participants also ranked small size as the worst one, so maybe the users have their own preference. Finally, we answer the first question about effects of crowd size. On performance, in cognitively demanding tasks, we found that medium size seems to strike a balance, which aligns with the Yerkes-Dodson law, which is moderate stimulation facilitates performance. When the crowd is too large, participants may experience attentional blindness, as reflected in both perceived crowd counts and their self-reports. In other words, the performance gains we observed appear to arise mainly from cognitive mechanisms rather than changes in subjective social experience. And for social presence, from small to medium size, there were minimal changes. However, in the large size condition, social presence significantly increased, which may indicate that the crowd surpassed the participants' cognitive load limits. And about the task. Task table significantly influence how participants experienced the virtual environment. And we observed many task-dependent effects. Looking closer at the patterns, simpler low-load tasks like spatial locomotion tended to support a richer social and immersive experience, allowing participants to notice and engage with the crowd. Complex high-load tasks, such as memory search, benefited from reduced visual distractions as participants focused on the task and largely ignored the surrounding avatars. Also, I want to acknowledge some limitations of our study. Our design was highly controlled to ensure internal validity, but that naturally reduced the ecological realism. And the avatars were randomly distributed, which sometimes created areas that felt denser than others, and many other limitations. We are looking ahead. There are several exciting directions. We could replicate this study with larger and more depth samples to strengthen the study. Integrating eye tracking or modeling local crowd density could give us a more precise understanding of how visibility affects perceived crowd size. Overall, our findings highlight the interactive relationship between task functionality and crowd perception in SVEs, suggesting that both task characteristics and crowd configuration need to be considered when designing immersive multi-user environments. Well, that's all. Thanks for your attention.
Thanks so much. Does anyone has a question or comment? Yeah.
I have a little question that the crowd was not having any kind of animation, right?
We use only 10 animations, and they customized, and that didn't show in the slides. But if you have any questions, please email to me. So why we only use 10 animations? Because that the more animations we think will introduce many other unnecessary indicators or other things.
I was just wondering that since was there any kind of other baseline or pilot study? Because is that crowd matter or just the complexity matters? If there is other kind of moving object is existing rather than an avatar, would the effect will be stay the same or different?
I'm sorry, I didn't follow your question. Could you speak?
I was just asking that the crowd is important because it's some kind of other human object, right?
Yeah.
But if it is converted to some other object that is just moving, like just a spear or other object, do you think that the effect will stay the same or it'll be different?
I got you. It's really a good question, and when we submitted this paper, the reviewers also had this question, And our answer is that why the avatars don't move or have other things, it's mainly to control the measures, and so we do have a really controlled environment.
Then let's quickly have one more question.
So you're saying that social presence
Yeah.
increases with crowd size, right? And
Yeah.
so do you know like what's the other threshold after? So you need how many people in the crowd to have this significant jump into presence?
We only tested the circuit size, and about the 40 size in 22.5 times 22.5 square. Yeah. And we didn't test many other crowd size levels. Yeah.
Yeah, I understand. Yeah.
But what I can say is that 就是in small size and medium size, the social presence is not very large, and only in large size. So it means it may have some. So the large size may surpass the participants' perception limit or other things.
Yeah. Thank you.
Thank you.
Yeah. Thank you very much.
Okay. Good morning, everyone. Okay, I'm very happy to be here. Okay, to give our paper presentation. My name is Saikun Wang, and let's start. Okay, stressful situations in public environments pose critical challenges for ensuring the safety and well-being of individuals. Unexpected and potentially life-threatening situations can lead to the evacuation of large crowds to ensure the safety of individuals within affected areas. Effective crowd evacuation is a critical component. Individuals gauge emergency situations through their risk perception. They visually gather information to interpret the situation and risks. The perceived cues will impact the decision-making concerning necessary actions such as evacuations, sheltering in place, or taking no action. Virtual reality provides immersive and realistic environments. It helps users prepare for crisis scenarios in controlled yet lifelike environments. In addition, it provides a safe space for learning from mistakes and building skills. Many factors influence human behavior, for example, active and passive crowds, and the sizes of organization groups. Active crowds engage and react to emergency situations. In contrast, passive crowds remain unresponsive. Visual attention in stressful situations help design environments that promote safety and clear decision-making. Observing others helps interpret unclear danger cues, but misallocated attention can negatively impact decision-making. Current organizational behaviors also influence visual attention. People strategically shift attention across individuals and environment groups to coordinate and follow social norms. Our contributions include the following 3 points. First, we provide insights into how external stressors affect visual attention during social interaction with individuals or groups. Second, analyze visual attention based on visual crowd behaviors, agitate and calm in emergency situations. And lastly, we compare visual attention allocation during normal and emergency scenarios. Here's a short demo video. In here, we design a virtual marketplace that the user need to collect 10 items, and in the normal phase, they need to collect 5 items. After that, there will be an emergency occurs. And in order to collect items, they need to interact with the pedestrians to ask for direction. And here we have a GI, and then assist the users to ask questions to collect the 10 items. Yeah, here's the vendor agent. And the user will ask the vendor, okay, do you have this item? And then if there isn't, this is the item, and then the item will appear on the table, and then the user can take it. And after that, the task list will update. And here, in emergency situation, there's a fire flat occur in the middle of the virtual market. Yeah. And then our research questions include the following. To what extent do the different types of virtual cloud affect visual attention behavior of users? The second one is, to what extent do the cloud types affect visual attention behaviors of users? And lastly, to what extent does the stressful phase affect the visual attention behavior of users as compared to the normal phase? So we examine how the reaction types and cloud types of virtual humans and simulation phases affect users' visual attention. And during the stressful phase, virtual humans have two states. One is in calm, okay? This is one condition. Another one is the agitated condition. That means the virtual human exhibits distress-related behavioral changes. Let's say walk in fast pace or show some fear facial expression. Now here's the experiment design. Okay, we have two between subject factors, reaction type and curve type, and one within a subject factor. That's the simulation phase. So all the participants will go through the normal phase first and then the stressful phase. In the normal phase, they collect 5 items. After that, in the stressful phase, they need to collect another 5 items. So we have 4 independent groups. All the participants go through this procedure. And then let's talk about the measures and analysis methods. So our goal is to analyze the visual attention of participants. So what are the view targets? They are pattern agents, vendor agents, conversational GUI, file, and virtual environment. And we use 2 types of measures, proportions of fixation time and proportions of fixation transition view target. So they provide a comprehensive analysis of visual attention, and also they review how time is distributed. And we use a mixed novel analysis under assumption that the normality and severity assumptions are satisfied. Otherwise, we need to perform the non-parametric analysis. So we can categorize this visual attention data into 3 categories: interactions with pattern agents, interactions with vendor agents, and the third one is navigation within environment. So we also collect the data for the normal phase, within the normal phase, stressful phase, and the entire simulation. So here's the result. As I mentioned, we have 3 components: interactions with pattern agents, interactions with vendor agents, and the navigation within environment. We found quite a lot of main effects and interaction with effects. So here, because of time, okay, here I just focus on some of them. Let's talk about the C1, okay, interactions with pattern agents, and we talk about the proportional fixation time, and we found an interaction effect for phase and cloud type. Yeah, so an interaction effect was found between the simulation phase and cloud type on the mean proportional fixation time on agents. Yeah, here. Yeah, and also in addition, in the normal phase, participants exhibit in a higher mean proportional fixation time on agents in individual condition than in the group condition. And here, a main effect was found in the reaction type on the mean proportional fixation time on fire, and so on. Yeah, please refer to our papers for details. I do not want to go one by one, okay? It take quite a lot of time in here. And the second part about the interactions with vendor agents, we also found kind of main effects, and so on. Yeah, for your interest, please read our papers for details. Let's summarize our major findings then. Yeah, first of all, in a calm condition, participants exhibit heightened risk awareness, spend more time fixation on the fire flat to assess environmental safety. They showed curiosity about the passive behavior of pattern trends and vendors. They increased fixation on fire and passive agents, and possibly due to the semantic variations. That's something that maybe people would like to expect to happen, but not. Because for the virtual humans, pedestrians, they do not react to the fire threat. In the agitated condition, participants focused more on the overall environment. They react to active responses from pedestrians and vendors to the fire threat. And then in a small group condition, participants distribute the visual attention more broadly, have a wider visual attention, visual allocation of attention. And in the individual condition, participants focus more on engaging with single pedestrian agents. They demonstrate heightened vigilance during their interaction with individual virtual humans. And lastly, here the result for between the stressful and normal phases. Participants in the stressful phase reduce attention to agents compared to the normal phase. They fixate more on pedestrians for information while they engage less with vendors. And they prioritized goal-direct attention. They aim to complete tasks efficiently and minimize interaction with vendors. And finally, here's the feature work that we like to develop. First of all, we like to develop a VR system, training system that integrates passive crowd scenarios to enhance situational awareness in ambiguous hazard conditions. And as you can see, since crowd composition influences visual attention distribution, the system should flexibly simulate various organizational behaviors. And lastly, the simulation model should integrate virtual crowds with diverse decision-making heuristics and varied attention shifts to improve the realism of evaluation simulations. Thank you for your listening.
Thank you. Any question or comment? Yeah, over there.
Yeah, thank you very much. It's a great presentation. A few sort of small questions. I didn't get it, sorry. How many participants did you have?
Oh, okay. Yeah, here. 64.
Oh, 64, okay, great. And I was wondering, actually, for your situation, since you also mentioned these different phases and different actions and kind of weird disconnects between a stressful situation and a calm reaction of the crowd, did you measure perceived realism of the situation slash like the evacuation scenario? Did you
Yeah,
ask
in
people about
fact,
this?
we collect quite a lot of data that in the pilot study we have some users to evaluate the realism of the scenario, and also at the end we have the archive feedback from the participants. However, unfortunately, because the paper limit, we do not include it. Otherwise, we have one more half of the pages more than that. Yeah, so
Do
unfortunately,
you have
we
any
cannot.
results or insights on this? How people evaluated this?
Based on the 7 Likert scale, points, we achieve for the realism of the virtual human fire environment, something like this, is about 5 points.
Okay.
4 to 5, something like this. Yeah.
All right, thank you.
Yeah.
Thank you for the talk. I can imagine that people react differently in stressful situations based on their background, personality, age. Did you investigate this too?
Yeah, we do not classify participants into these kind of different groups. Yeah, we do not collect their background about whether you have experience in this guy's scenario, evacuation or something. In the pre-questionnaire, we do not do it. Yeah. And of course, the reason that we do not do is that if we ask the question about this beforehand, maybe we pose a high bias that let the participant ready for this kind of scenario, so we do not ask these kind of questions. Yeah.
After?
And of course, in the future, I think after the participants have done this kind of experiment, and then we can ask the question and then do a kind of subgroup analysis. That will be really helpful. Yeah. But we do not do it in here. And you can see we just have 64 participants. I think you need to have 100 something. Maybe at that time you have one group that's no experience in evacuation, one group is somewhat have this kind of experience, another one that's have this encounter this kind of situation. I think you need to have at least 3 groups, I think.
Thank you.
Let's have one more question.
Hello, my name is Minoo Song from KAIST. Thank you for your great talk. And this is a follow-up question to the first question. Actually, in these crowd behaviors, I believe that there were several previous works on crowd behaviors, crowd behavior modeling based on fluid dynamics. And especially in this emergency evacuation scenario, I believe that we should correctly model the real human behavior into virtual humans to get the correct results. And I wonder, how does the virtual humans correctly model human behavior in your experiment cases, especially?
Yeah, thanks a lot for your question. Okay, here we just in a common sense that whenever we have two mode, right? Okay, for the first mode is the normal phase. Okay, the virtual humans just walk naturally. Okay, so this kind of data that we can collect from the literature. Okay, however, in the emergency situation, I believe there's quite a lot of diverse behaviors that can attribute by the real human. And unfortunately, we do not really model a kind of diverse behaviors in here. Here we just focus on, okay, in the stressful phase for the agitated potentials of vendors, when they encounter this kind of emergency situation, they just walk faster or something, yeah, and then show some kind of worry, a negative facial expressions, something like this. And I believe in the real life, there are other kind of scenarios. Let's say, for example, some people may shut, right? Okay, and some people may be too scary about this situation and then walk. Really sorry. Okay, yeah, something. I think there's a lot of future that possibility for all of us to devote. Yeah, thanks.
Okay, thank you.
My name is not Julia. That's okay. I'm Benoit. Julia is a wonderful postdoc scientist in neuromove in my institution, University of Montpellier. But like she couldn't make it, so I flew here and I'm giving this talk. This is a joint presentation with DFKI, Kaiserslautern in Germany. And so we are interested in togetherness and connectedness in general. And here is my vision, here's my quest. This is a thing that we want to understand, right? Both in physical space and in VR. And it's fascinating to see, this, like the feeling of togetherness, like the happiness, of these people being together. And in a literal sense, feeling connected is embodied in synchronization, right? So we feel like this connectedness when we are in sync with each other. And there is this wonderful relation between synchronization and connectedness. So synchronization, you need two things for synchronization to happen. You need systems, two or more, being like more or less similar to each other. And you need a coupling function between them, right? This is true in physics, this is true in biology, this is true in like all kinds of situations. What's also interesting is that the more similar the systems are, the easier it is, for those systems to get in sync. And so synchronization occurs through a coupling function, which is like multisensory, it's visual, it's auditory, it's all kind of thing. So we're trying to understand this type of situation, both in physical space and in digital space. And I'm going to give you a short presentation with like one or two experiments where we're trying to manipulate those components in order to understand, this type of situation. So this is pretty poor compared to what I showed before, but basically this is the type of experiment we're doing in the lab. So, people are in sync with each other, either explicitly or implicitly. They have to synchronize, it's phase synchronization in this particular case. Here is a more controlled situation where, we can control for facial expression, removing all the emotional qualities which are affecting, synchronization. We can also block the view in order to prevent, the direct dyadic type of interaction between those. I mean, all kinds of manipulation are possible. And now we want to move that into VR. So this is very simple VR. We're using like a few MetaQuest Pro HMDs, and we're doing this type of situation where we're trying to solve some of the challenges. So capturing, rendering is one of them. Of course, those HMDs do not have the same field of view, as the physical space, and the end-to-end latency in the action perception loop. The IK, type of approximation that we have to do are illustrations of those challenges that we have to face. So we want to compare, the physical space and the digital space in those type of situations. So we have a European project. It is called ShareSpace. And basically what we do in share space is this type of situation where you have like a group of participants doing this type of synchronization. They're interacting together. And basically those human participants, in our jargon, we call them L0. So they are human participants, they're fully equipped. And sometimes they're interacting, with each other. And sometimes they're interacting with like a digital character. So digital character can be L1, level of autonomy 1, which basically means they are like human-driven avatars. And sometimes we can increase the level of autonomy. So for instance, L2 avatars, they have a certain amount of autonomy. So for instance, they can change their frequency or amplitude of motion compared to what the L1 are doing in order, let's say, to increase synchronization, therefore connectedness between them. Or we can populate that group of participants with some fully autonomous avatars, we call them L3, in order to see whether you can replace a digital character by an AI and see whether that changes, the relationship in the group and therefore the connectedness. This is the kind of thing we are interested in. Today, I'm going to focus only on the L1. ISMAR next year, or in 2 years from now, you're going to hear more about L2 and L3. So this is like proof of principle experiment, but we have like ideas behind in terms of the natural scenarios. And we have work in sport, in health, and in art, where we're trying to instantiate those kind of ideas and results into more like real-life situations. So I'm going to show you a few results on this experiment. So the challenge of capturing, with the MetaQuest Pro is one of them. We were pretty happy when we started collecting those data where, when we compare like the tracking, the MetaXR plugging in the HMD to the gold standard Vicon, basically for 3 participants, you can see like the tracking. So basically those people are doing these types of very simple arm movement. And you can see that the tracking is pretty good, which is good news because you can go out of the lab, we can go in like natural spaces and do those experiments, in a more natural circumstances. So we're doing this type of situation where you see here, 3 participants in the lab, and this is the VR equivalent. This is what they see in their MetaQuest Pro. And we're doing experiment where, for instance, we have a solo condition. So each of those participants are doing this solo movement. Or we have a social context. Basically, they're doing this type of experiment without any instruction to synchronize. It's just an implicit type of social synchronization task, with also a synchronization condition where they have explicitly to synchronize their body movements, and we measure kinematics, we measure synchrony. There are models like phase oscillatory model to measure synchrony, and obviously connectedness is key in these particular types of experiments. So let me show you like 2 or 3 results here. So here is the order parameter of the Kuramoto model, which is basically the group synchrony, and you see the time dynamics of that synchrony, going up and down. But it's mostly, if you look at the result, group synchrony is pretty good, in the situation where people are instructed to synchronize. So they're just like following the instructions that they have received. Now, if you look at the iOS, which is a measure of connectedness, basically that's the inclusion of other in the cell. So how much I see other people in my cell, that's a measure of connectedness. You can see that, it goes up as other social context goes up, which, is pretty good for us. And then if you look at individual kinematics, the way they're achieving this group synchrony, you see that, in VR, people are slowing down their speed, and they are also, this is going to be more evident in the next slide, they're also increasing a little bit their amplitude. So they're changing their individual kinematics in order to, reach that this synchronization level. Now, we also are interested in comparing, as I mentioned before, like the real situation together with the virtual situation. And so if you compare those 2 types of situations, in different experiments, then you have something like this. So group synchrony is as good in VR as it is in a physical space, which, is pretty good. So we can induce togetherness, in VR pretty much the same way as we can do it in real-world situations. We can even increase the feeling of togetherness in VR compared to physical world. So that's also good. But if you look at the individual aspects, you see some changes. So the movement frequency, so the speed in that circular movement, goes up, with the social, in the social context, in the real world situation, but it goes down in VR. So people are slowing down in VR, and it's probably accommodating some of the technical challenges, the latency, the lack, the smaller frequency, all kinds of technical aspects. And so people find ways to cope with that situation, and in this particular case, this is by decreasing frequency and also decreasing amplitude. So the individual contribution in order to achieve the same level of synchrony is different in VR and in a real situation. This is the kind of thing that we're trying to document. We are now moving toward L3. So now what we're doing, I'm not going to have any, I don't have time and I don't have all the data at the moment, it's to replace one of the L1 by an L3 just to see whether if you do an L3, whether that changes the entire group dynamics in those situations. So to summarize, I think I'm reaching my limit here. We are interested in looking at the effect of group synchrony on both the way people move together in sync and in the consequences for connectedness. We found that group synchrony is modulated by the coupling and obviously by the instruction, sort of mirroring what exists in real-world findings. We also found that people manage individually to find a way to adapt to the technical challenges in order to cope with those technical aspects and achieve the synchronization. And that's probably interesting to scale up to more people in a group. And we're also thinking moving to AR and have this kind of hybrid situation where you have a group with real participants, L1, L2, and L3 avatars sort of interacting together to promote connectedness. Thank you.
Thank you very much. Any questions or comment? Yep.
Thank you very much for interesting talk and experiments. I'm wondering, because you showed that in VR, people feel even more connected. It's kind of surprising. Can you elaborate a little bit more?
Yeah, we were surprised ourselves when we found that. I mean, it is significant, this particular situation. Let's say it's as good as it is in real life. In this particular case, it is even better. I think it's related to the sort of context in general. So those participants know they're going to be in VR. They're sort of, they're volunteer. They come to experience the VR. It's kind of fun for them to play with this VR. Those are psychology and kinesiology students, and they're happy to be there. So I think that sort of explains. I wouldn't bet, we have that result all the time.
Yeah, so this is yet like a proof of the wow effect, yeah? That we, to some extent, should remove.
I mean, possibly. I cannot really answer. We should do like two or three times to that, or take the same participants when they are more experienced with VR to see whether this is really a sort of result. I wouldn't bet this is exactly.
Thank you very much.
Okay, question.
Oh, thank you for this most interesting presentation. In one of the slides, you suggested how you feel people getting together, and have you looked into the effects of physical or virtual distances between participants? Because in a football match, we tend to be very close to total strangers. And I wonder if that proxemics would play a factor in these effects that you report.
Yeah, very good. So we have not looked at that in those particular experiments, but we've done many of those experiments in physical space, and it scales down with distance. Right? So when you are very close to each other, synchronization, gets up, and connectedness goes up as well. So there is kind of correlation between together and synchronization scaled by the distance.
So are you talking about both physical and virtual spaces?
Only physical. We have done those experiments in the real world. But I guess we should have the same type of result. Yeah. The farther you are, the less connected you are. Yeah.
I'm curious about that. Thank you very much for your presentation again.
Yeah, let's have two more questions.
Hello, thank you for your talk. There's a really interesting findings. I wonder, you showed in the beginning a slide with some ways to apply those insights. I think there was a slide with art and health. If you have time, could you maybe go into that a little bit? What kinds of application would be possible according to your...
So let me focus, because of the time constraint, on two of them. So one is health, because so I'm working with the Barcelona Hospital La Défense, which is one of the largest hospitals in Spain, where they are having a big like case for low back pain. Did you know? I didn't know that synchronization raises pain stressors, and so people they feel less pain when they are in sync with each other. Wow. So we're using this situation, to alleviate pain a little bit. So that's one. And for art, there is this huge Ars Electronica festival in Linz in Austria every year. We were there like 2 weeks ago, mid-September, that was months ago. And we're doing this performance with like scientists and artists using the share space, synchronization game where, people have to find the right spot. It's a big cave, as Ars Electronica. They have to find the right spot, and they have to find the right motion to be and be in sync with each other. And when they do so, then that creates a kind of shape, a 3D shape, both audio and visual. So they have to discover, like we pick up people in the audience, and they have to discover where to be and how to be in sync in order to produce that performance.
Fascinating.
Yeah, let's quickly have one more question. Sorry about that.
No, I guess the previous one or the next one with the results on, yeah, this one. So if people behave individually, they speed up in VR. But
No, they speed up in the real world, which is like here. They speed up in the real world, but they speed down in the VR.
but the first column is comparison between real world and
Yeah, so
VR.
this is real world in blue, and this is VR in red. This is frequency, so the speed. So basically, when they are explicitly instructed to synchronize, they slow down.
Yeah.
So they adapt to the technical challenges of the VR
Mm-hmm.
by slowing down, whereas in the real life, people speed up because those technical aspects, with this, or they are different. So there is a sort of positive loop, speeding up in real life and slowing down in VR. It's basically to show that they are like a sort of adapting to the technological context in order, to produce the same level of synchrony.
Okay, thank you.
Thanks so much. I'm sorry.
Can you hear me? Yeah. Hello, my name is Myungol Jung, and I'm an assistant professor at the Department of Clothing and Textile at Hanyang University, and I'm here to present our study, Can People's Brains Synchronize During Remote AR Collaboration? And I'm excited to share my work with the ISMAR community. And these are our colleagues, Dr. Jae-hwan Yu, me, and Professor Kwang Kim. And I'll start my presentation. I believe many people are familiar with video conferencing, which enables us to remotely interact with each other and form a telepresence during the remote interaction. And this video conferencing is currently widely used in the various fields in modern society. However, video conferencing has its limitations that there are still a big gap compared to offline face-to-face interaction like we are doing right now. So many researchers, like the ISMAR community, have put in a lot of efforts in developing more advanced methods to match this kind of remote interaction to the face-to-face interactions. One of the advanced method is AR-based remote interaction, which are capable of enhancing the spatial information exchange, and it can provide more immersive experience during the social interaction. Furthermore, AR-based remote interaction can provide a co-presence that is similar to the face-to-face interaction by displaying or projecting the opponent's avatar in my space. Based on these popularities in AR, researchers have also been interested in brain-computer interface, or BCI, in AR. For instance, McKendrick
used a Google Glass with the FNS device and shows that the AR-based wearable reduced workload and enhanced a situational awareness in navigation tasks. And Aftergan also used a Google Glass and FNS device to find that brain activation-based adaptive notification in AR reduced mental workload and improved a focus. Finally, Hu used a HoloLens and FNS device for developing an AR visualization system for monitoring the pain intensity and localization of an individual. However, these previous studies on AR BCI focused on only individuals' brain activation, which is not suitable for remote AR interaction between people. So in this study, we aimed to extend this AR BCI into social AR in this study. To utilize the BCI for social interaction, we have reviewed studies which have focused in social brain activation in offline, face-to-face in situations. I'll just refer to face-to-face as F2F. Previous BCI studies like this men and women have found a phenomenon that interaction partners' brain activation have been synchronized during a social interaction, which is called a brain synchrony. And studies have also found that this brain synchrony of the prefrontal cortex that is related to both cognitive and emotional functions have been increased when people have engaged in a collaborative task. For example, Cui has found that the brain synchrony was higher when participants have collaborated in the middle. You can see the figure in the middle. Collaborated to click the button when the button has turned into the green, compared to when they have competed to click the button. And Nguyen has also shown that participants' brain synchrony was significantly promoted in the collaboration task rather than individual tasks. These face-to-face studies have shown that brain synchronization can occur during the collaborative work. However, the effects of this collaborative work on brain synchrony between partners in remote AR interaction have not investigated yet. Based on this brain synchrony on face-to-face studies, researchers have attempted to explore the brain synchrony in remote computer-mediated interaction settings. Like Schwartz, who showed that the brain synchrony in the video conference was lower than that of the face-to-face, and Gumillar and Barde have shown that the brain synchrony that has been induced by the bodily behavior was similar to the face-to-face in the virtual reality. These results indicate that there can be similarities as well as differences in brain synchrony between computer-mediated interaction and face-to-face interaction. So in this study, we aim to compare the brain synchrony between the remote AR interaction as well as face-to-face interaction. So in this study, we have conducted 2 studies of remote AR brain synchrony under these 3 hypotheses. First, brain synchronization can be enhanced during the collaborative work through the remote AR collaboration interaction. And secondly, the relation between the brain synchrony and task performance would differ between collaboration and individual work. Finally, we assume that the remote AR interaction would demonstrate a similar activation of brain regions as that observed in the face-to-face interaction. So I'll proceed to the method that has been used in my study. We used a remote 10-gram puzzle task to facilitate the remote interaction between the partners. Participants were asked to move each 10-gram puzzle in color, by the way, and to accomplish the 10-gram puzzle goal that is displayed as a gray object over there. And participants were also asked to solve the puzzle as much as possible during the task time of 2 minutes. There was 2 main conditions in this study, which is collaboration and individual. In the collaboration condition, two participants could see each other through the AR device as a form of an avatar that has been matched with the participant's gender, and collaborated to solve the 10-gram puzzle together. However, in the individual condition, they solved the puzzle while blocked by a physical wall so that they could not see each other, and they have solved the puzzle independently. And we have measured the brain synchrony in this experiment using two functional near-infrared spectrography, which I call FNIRS. And this device measures 15 channels in your prefrontal cortex. And the actual brain synchrony value was calculated through a wavelet transform coherence technique, and each channel-wise value was recorded or calculated between 0, which is a low synchrony, and the 1, which is a high synchrony, and the average value of 15 channel was used for the analysis. And we also measured the task performance. In the collaboration condition, the total number of completed puzzles between two participants were used. Whereas in the individual condition, the average number of the completed puzzle between two participants were used, and we also conducted a Pearson's correlation analysis between the brain synchrony value and the task performance. In our study 1, we have focused in comparing the brain synchrony between collaboration condition and the individual condition in the remote AR environment. The results of the study 1 have indicated that the brain synchrony was significantly higher in the collaboration condition compared to the individual, which supports our first hypothesis that the brain synchrony can be enhanced during the collaborative work in remote AR interaction. And the results of the correlation analysis indicated that there was positive correlation between the brain synchrony and task performance, which is displayed as a red chart. And this kind of positive correlation has only occurred in the collaboration condition, but not in the individual condition. So this result supports our second hypothesis that the relation between the brain synchrony and task performance would differ in collaboration and individual condition. However, in the study 1, we only measured the brain synchrony and task performance in the remote AR collaboration or remote AR interaction. So to verify our third hypothesis, we have conducted a second study where we measured the brain synchrony between two participants in the offline face-to-face interaction. And we have compared the result of the study 2 with the remote AR group in the study 1. We found that the face-to-face group showed higher brain synchrony than AR group, which is indicated as a red arrow and red box. However, the tendency of the collaboration condition, which showed a higher brain synchrony compared to the individual condition, remained same tendency between the AR and face-to-face groups, which is indicated by blue arrow and blue box. And as there were no interaction effects between these two main effects, we assume that the remote AR and face-to-face groups showed a similar tendency. And to further investigate the difference between AR and face-to-face groups, we conducted a post-hoc analysis according to the 5 PFC regions. And we found that these differences between AR and face-to-face have been driven by the area of bilateral OFC, which is a green region, and the FPC area, which is blue region. We speculate that these differences have been driven by the virtual avatar used in our study and the task in the current study. For instance, the virtual avatar used in our study did not reflect the eye movement of the opponent. So this could have made the difference in the OFC region. And as the 10-gram puzzle task does not require much of a verbal interaction, So this could be the cause of the differences in the FPC region. Despite this difference between AR and face-to-face, the correlation results showed a similar tendency between AR and face-to-face groups, that the positive correlation between the brain synchrony and the task performance was only observed in a collaboration task, whether it was remote AR or offline face-to-face. So these results of the study 2 partially support our third hypothesis that remote AR interaction would demonstrate a similar activation of brain regions that have been observed in face-to-face interaction, as there were similarities as well as differences in brain activation between AR and face-to-face. Before I finish my presentation, I want to summarize our contribution. First, we have empirically demonstrated a neural evidence that brain synchrony have been enhanced in the remote AR collaboration. And secondly, we have confirmed that there is a positive correlation between brain synchrony and task performance in remote AR collaboration. And finally, we found that there are similarities and differences between remote AR and face-to-face interactions. And the similar tendency in the brain activation between collaboration and individual condition was similar between a remote AR and face-to-face, whereas there were differences in brain regions regarding the social feedback, where face-to-face still showed higher brain synchronization compared to the remote AR. Thank you for listening, and this QR leads to my homepage, and you can contact Jae-han Yu or myself for the details of my study. Thank you very much.
Thank you, Mong-yeol. Let's have 3 questions. Yeah, you must be last one. Yes.
Thank you for your presentation. Great work there. My name is Maha Sajid. I'm from Virginia Tech, USA. I just wanted to clarify that in your AR condition, the individuals could not see each other, but in the real world condition, they could see each other in the individual condition?
Yeah, in the collaboration condition, participants could see each other, however, not directly to opponent, however, they could see their opponent as their virtual avatar in the collaboration condition. However, in the individual condition, the participant could not see the opponent, and they could not see the opponent's avatar as well. So they are solely left to the AR space to solve their own 10-gram puzzle.
Okay, I was wondering if it would have been a more fair comparison between face-to-face if they could see, if they were still doing their individual tasks, but could see each other's avatar, because that's what happens in the face-to-face condition, right? They could see each other, but they were doing their individual tasks. Is that?
Yeah. So to match our remote AR condition, in the face-to-face condition, we have physically blocked participants to see each other using that wall. Yeah.
All right,
So
I
they could
missed
not
the-
see each other. Yeah.
Okay, that makes sense. I missed the wall. Thank you.
Thank you.
Okay, the second one. Oh my God.
Thank you for the talk. I have one question. So in collaboration setting,
Yeah.
you can, both of the participants sees the same 10-gram puzzle
Yeah.
in the same progress, right?
Yeah. Yeah.
While individual condition, the 10-gram, they have their own 10 grams, right?
Yeah. That's
So
correct.
Couldn't it be possible for the brain activity be affected by the visual? Because in group condition, collaboration condition,
Yeah.
both of them are looking at the same visuals, while the individual conditions have their separate visual stimulus.
Yeah,
right?
that could have been affected, but to control that kind of visual aspect, we try to match the sequence of the 10-gram puzzle between the collaboration and individual. However, that might have been affected. So we have conducted another analysis that so as that kind of visual aspects should not affect or have not, to prove that have not affected the result. So what we did was to, it's not here, by the way. So what we did was to compare the brain synchronization in the collaboration condition but with the different pairs. So in this case, we think, or we can say that that kind of visual aspects are controlled in the collaboration condition. However, in that case, we could not find any other evidence that that the brain synchrony value has been related to task performance because, in that case, by calculating the brain synchrony between the people in the collaboration condition, but not in a pair, for those who have not collaborated, that has resulted in similar result that is shown in the individual condition. So we have kindly concluded it as that kind of visual aspects have not affected this result, but as you said, that kind of visual aspects could have an effect in this kind of brain synchrony result because the brain activation is kind of trickier. So that can be our future research direction. Thank you.
Yeah, one actually short comment about the visual synchrony.
Yeah.
Actually, in a collaboration task, you use a engram device, right? So engram devices, AR glasses, right? While the individual cases or non-AR cases, not wearing anything, right? Participants.
In individual cases, they wear AR devices as well. So the configuration settings in AR was similar between collaboration and individual condition. However, in the face-to-face condition, I believe that they did not wear that kind of glasses, or I'm kindly confused. So, yeah, they did not wear that kind of AR glasses in the face-to-face. So that could have been, that could have driven the differences in brain activation between the two groups. So it should be verified in the future study.
All right.
Yeah.
Thanks.
Thank you very much.
One more question. Let's have one more question. I will keep him here. After this session, you can ask your question again.
Okay, so just like I have a lot of questions,
Yeah.
but you said that the task did not require any verbal communication, right?
It does not require participants to actually speak and do that kind of thing, but naturally they spoke a little bit.
Okay.
However, they have focused mainly on solving this 10-gram puzzle in the.
Yeah, but in AR, because they were remote, were they able to communicate as well? Were they able to talk?
Yeah, they were able to talk.
So like in this, like with an
yeah,
audio
like a Discord
call?
or that kind of verbal communication, remote verification was able in the remote AR condition.
So even though they didn't see the avatar, they could still hear the other user.
Individual condition, they could not speak with each other.
Okay.
Yeah.
All right.
Thank you.
Let's conclude this session. Thank you all audience and all presentation together.